Welcome, everybody. Daniela, welcome again to the show.
Thank you. Thank you, Khawaja. Always a pleasure to chat. I hear we're talking about low latency inference today.
Ultra low latency inference.
Ultra low
I
latency.
feel like low latency sounds fast, but ultra sounds faster.
How fast are we talking?
In the world of inference today, people are talking about time to first token being in the hundreds of milliseconds. And that's exciting. But the two areas that I care about are sub-second and sub 250 millisecond full inference. So imagine if you can get 20 tokens out in 250 milliseconds, what kind of new applications become possible now? Where are the things where you can inject inference that you just couldn't before? And I think that's what's required for the world to evolve beyond just the chatbot and knowledge bot use cases.
I was going to bring that up. If I'm using a chatbot, I can't really discern the difference between a 500 millisecond response and a 100 millisecond response. So why does that matter? What are you thinking?
To be fair, most users can discern the difference, but there's a lot of visual tricks that get played with the UI. We'll have your draft model say something really silly for the first sentence so you can make it look like you got an answer really fast. And then there's things like streaming that are happening, so it looks like it's more interactive than it really is. But you recently sent me a link to ChatJimmy, which is running on Telos. And can you see the difference when you ask that a question versus ChatGPT or Claude?
Yeah, I can. Well, I think for me, it's that I'm used to, like, I start reading the words that are streaming in. But on ChatGPT, I feel like the answer shows up before I'm done hitting enter. I mean, it's obviously physically impossible, but it feels instant.
It does, right?
It's the entire answer. There's no streaming.
Yeah. Yeah. And I think if anybody hasn't experienced what that feels like, we'll put the link in the comments. But really, if you want to feel the difference that a fast response make and the level of interactivity in your app, like it's really worth trying it. And then you start asking yourself this question of what else can I do if my inference response was so much faster? The LLMs can help you reason, and you can put it in the control path. So recommendation systems can suddenly employ full-blown LLMs if you can run the entire inference faster. You can rewrite prompts faster. You can run your feature stores. You can do anomaly detection with LLMs if it were faster. And even with coding today, I feel it's still really fast. That Claude code can go out and generate weeks worth of code in a matter of 10 minutes. But why should it take 10 minutes?
Yeah, I recently had someone actually tell me this exact thing at a company that work on like low latency AI inference. Is people are amazed that you can give your coding agent a set of tasks, go to bed for 8 hours, wake up and have it all done. That's amazing. And trust me, it is amazing. But I think then it sort of begs the question, why does it take 8 hours?
Yeah.
Right? Why do you have to wait those 8 hours? Why do you have to line up a set of things and then wake up to find it working? Why can't it just be instant?
Well, you see people doing vibe coding on 8 different tabs at the same time. Part of that is because the inference is just taking that long. And when the iteration loop becomes really, really fast, then you can focus and get something out the door, and you can be more concentrated on that specific problem as well. And as we start thinking about what does it really take to enable low latency inference, I mean, the most obvious thing is, well, we'll need better models that can react faster. But there's a lot more that goes into it than the model itself, right?
Some of the pushback I've heard about is, well, my bottleneck is not, in the code that I'm writing, right? So if the inference itself, if the hardware itself, the model itself, like you said, is just that slow, does it matter that everything around it is optimized down to the dime? I think the reality is the inference itself will become faster. I mean, in fact, it has, right? You just mentioned one company, Telos, that came out and built this demo and made inference instant. There's a lot of other companies, including, NVIDIA doing an internal optimization on their chips. Cerebras is another example of a company that has not 20%, not 50%, but something like 10x faster.
Yeah.
And when that happens, the other stuff surrounding the inference starts to show up, right, in terms of performance bottleneck.
For the viewers who may not know, Telos is a company that's building an ASIC for the Llama model. So for that specific model, it's gonna be really, really fast. Cerebrus is just
Literally burnt onto the chip.
yeah,
Yeah.
yeah. So it's like as fast as you can get. And then there's companies like Cerebrus that are and Grok that are building custom SRAM chips that can that can run a lot of models, like a very heavyweight model on the same chip. But the problem is that inference traditionally, we have been complacent as a society where we accept slow inference. And slow inference has masked a lot of the problem in the rest of the ecosystem, whether it's the routing, whether it's the data collection side, whether it's the KV caching side, because the model and the hardware had been so slow in the past that all of these things were in the noise. But as the models get faster, as the hardware accelerates them, a lot of this masked capability, this masked bottlenecks, they start to percolate up and they become the new bottleneck,
So your
even though
software is slowing down your hardware?
yeah, and that's I think the transition that we're right at the cusp of, because cheaper models, faster models are going to improve in quality, and really good models are going to improve in speed because hardware is starting to ramp its way up. And now your data access becomes a big part of it. Your data placement becomes a big part of your performance bottleneck. And that's why it's so exciting to be in a performance-oriented company right now, because I think this means that we're finally in business because latency suddenly matters. And
Yes.
that's the
Yeah.
sweet spot that we want
Ultra
to
low
be in.
latency suddenly matters. I mean, it's not really that dissimilar to the sorts of problems we've been solving in the traditional non-inference, but
Mm-hmm.
sort of a data storage world.
Mm-hmm.
The data storage engine itself was I/O heavy. The model itself is now compute heavy. I/O got a lot better over the
Yeah.
years, and
Yeah.
now compute will get better, right? If we believe that that's inevitable, then all the lessons that we learn around it are applicable. What can you say about, for example, the similarities in something like routing?
Routing itself is a pretty solved problem as we learned recently. And authentication and actual routing, those are very easy problems. Everybody builds their LLM gateway really quickly. Where things get really complicated on the routing is where the data placement is and being aware. For instance, NVIDIA does a lot of work on the Dynamo side on being KV cache aware in terms of where you route the data. And they give you session stickiness to optimize for your KV cache hit rates. But now the networking becomes really, really important as well, because maybe you don't want to go to the same host that served this particular customer the last time because you're having a load leveling problem. And the one of the problems that we spent a lot of time solving on Dynamo and on Momento was how do you level the load across the storage nodes? And this problem is a lot more acute in the GPUs because GPUs are way more expensive and the use cases are a lot more spikier and more sporadic. So load leveling in GPUs becomes a huge problem when you're trying to optimize utilization. And if you have to maintain session stickiness, then you are going to have a really hard time leveling the load. And this is where a lot of the work that we've been doing on zero copy side and network optimizations and data placement, these are the kinds of things that help you level the load on the storage side, and we are applying the same tricks now for KV caching on the GPU side.
How do you really get that much data from one node to the other node as fast as possible? Right.
Well, I can tell you what slows things down today on the more naive implementations of KV cache. There's a whole lot of copying that's happening,
Mm.
right? So a lot of the layers are written in Python, and then you're making one copy on the C or Rust land, and then you're copying from kernel to the C land, and then you're copying from C to Python, and then from Python back to the GPU. The zero copy is a tried and tested strategy in the web servers, the databases, and the caching world. And using things like Nixel to go straight from the SSD that's on the node to GPU without making any copies along the way. That becomes very, very crucial. A lot of these data centers that we play in, AWS, GCP, um, a lot of it is just Ethernet based. And you're doing a lot of transfer on on Ethernet via TCP. So normally your TCP windows wouldn't really matter in these data centers if you have a really fat pipe and a low latency. But now we're talking about hundreds of gigabits per second of network that you're trying to saturate. And this is where even little things like your TCP window being warm, having the right buffer so you're not reallocating every time that the data is growing, having fixed size buffers, doing zero copy on the server side and then on the GPU side so that the data can go from network to GPU without any additional copies. All of the same tricks that we have been employing to get to the 100 microsecond latencies for our traditional caching business, they start to have meaningfully larger payouts and dividends on the GPU side for performance and for just making KV cache more plausible.
The interesting thing that I've learned thus far from working on the KV cache optimizations is not only is a lot of the lessons reapplicable from our traditional database caching lessons, it's not just one thing. You don't have this moment of reckoning where you're like, oh, I'm able
I
to
flipped the fast switch.
Exactly. Exactly. And when you talk to other like incredible engineers about this, especially engineers who traditionally worked in distributed systems, these are not new concepts. We're not inventing physics here.
Yep.
But it's just a slew of little things that build up. And every time you optimize one thing, you move the needle a little bit. Everything needs to be right. All the roadblocks need to be cleared from the GPU down to the disk. And once you get there, then you're suddenly looking at a much more meaningful improvement. And that was sort of a aha moment at the end of a very long journey where it's like there's not just one thing I can point to and sort of
well, then sometimes there's regressions, right? You change one thing that makes one part of your stack fast, but then it slows down the other stack. In some cases, we've learned that we've introduced more race conditions by making one part of the stack faster, and that's caused degradation. But part of as founders, one of the things that I feel luckiest about is our team is very good at clinical characterization. I think that is so crucial in being able to optimize these new stacks because the stack itself is evolving so quickly. It's not just the parameters we're changing. There's new capabilities that are coming out left and right. And we got to evaluate those capabilities at the pace of like NVIDIA's roadmap. And we have to be able to characterize and quantify, well, did this make things faster or is it making things worse? Or is it exposing a bottleneck? So just that muscle that we have developed around clinical characterization about repeatability, and then all the muscles that we've been working on really tuning the underlying internals of a system at the kernel level, tuning the threads inside of like all the parameters inside of Tokyo and on the Rust side, and then applying and learning now a bunch of new skills on how to apply all this to on the GPU side. It's very gratifying.
I remember there was a specific instance when you were doing KV cache benchmarking, and I think there was a moment of frustration when you found that the data was not representative or representative of prod. What was that example, if you recall?
I remember two things. One was, well, the glide driver for Valkey. So a lot of this KV caching work is done in Python, but the glide driver for Valkey has a Rust underpinning. And at a high level, you would say, well, it's Rust underneath Python. Of course it's fast. But it turns out that no, that doesn't make things faster. In fact, it makes things slower because that just wasn't the bottleneck to just do the data transfer in Rust. The bottleneck was at that particular time, it was the global interpreter lock for that version of Python. And even if you have multi-threading inside of Rust, but if your command side is processing one request at a time, you hit a bottleneck and then you're not reading data off the NIC fast enough, which then erodes your TCP window and so forth. Then we also learned that because you wrote it in Rust means, well, you have to do an extra set of copies. And that's really, really bad. Like you would think that memory copy is so much faster than copying something off the network. But the reality is that for larger objects that are in the multi-megabyte, memory copy in some of these situations also means that you're waiting for the entire multi-megabyte item to be copied before you consider it to be done. You're not streaming it to the GPU. So every iteration is like bounded by you making multiple discretized copies of these multi-megabyte objects. So that memory copy, which sounded really cheap, and especially because the underlying aspect is getting you some rust, actually slows things down. There were these other parts where, some of the tutorials were about you run a model with dummy weights. And
I
if
see
you,
that a lot, actually. I've done some. Yeah.
yeah, and this is, this is the exact opposite of clinical characterization, right? Because I read the tutorial and I did everything the way it was described, and I ran something with dummy weights, and I was like, maybe I can just apply Z standard compression on the KV cache. And I thought I found the fast button because, man, for dummy weights, your tensors compress like that. And I was like, wow, I've solved this problem. I'm getting 80% compression. We're done. And then you find out, nope, this was with dummy weights. And then you turn on the real weights for, whether it's Gemma or Quen, and suddenly your compression efficacy goes down the drain. And so
And you're
it's,
paying extra compute for that.
and you're paying way extra compute. So you end up spending more compute. When there's more entropy, it actually takes you longer to do the compression as well. So a lot of these things, having real world data. So we actually went and generated a corpus that has medical docs and legal docs, so that we can have more representative real world data generated by open weight models, so that we can characterize these optimizations we're making without dummy weights or dummy content.
Yeah, I think benchmarking, and specifically clinical benchmarking, is an underappreciated art.
It is. And if you ask ChatGPT to help you, or Claude Code to help you make the benchmark clinical, it thinks you're making it wants you, that you want it to make it more medical. And no, I learned the hard way that clinical characterization to an LLM sounds like something that happens inside a hospital.
What are some of the principles? Let's say you're approaching a completely new framework, a piece of software, and someone's asking for your help. Hey, I need to improve the performance of this. What are some of the questions that you ask immediately to kind of get somebody thinking about this clinically?
I think A/B testing, while only changing one parameter, is super crucial. So we're working with a few folks deep in the KV cache side that wanted us to assess the efficacy of Redis versus Valkey. We're comparing Redis 8.6, Valkey 9. And the first thing you want to pin there is, well, I'm going to do it on the exact same pairs of hosts. The same host is running Valkey, the same host is running Redis. And then I'm going to have a different host that is running the GPU and is going to test the various configs. And then you get into other artifacts like, well, maybe there's some warm up, or maybe there's some throttling that's happening. So you run a few runs of the test where you sometimes are running Valkey first, sometimes you're running Redis first. This is to make sure that there aren't any artifacts that are being introduced. And you got to repeat all this as you sweep the parameter space to try various parameters. Like IO threads in Valkey 9 are amazing because they prevent you from having to copy large objects. You can start streaming the object without making a full copy. So first you hold the exact same parameters, you use the exact same client, you use the exact same server, and then you do the sweep to see what parameter really works. By the way, if somebody's already done the benchmark, one of the first things I do is I try to generate the same results they had, so that when I run my experiments, I can actually assess, did I make things faster? And am I measuring it the same way that these folks were measuring it? After that, you got to start diving in, like getting, this is your cup of tea, like observability.
Yep.
What is happening, and tracing, like what, maybe it's not that my entire 5 gigabyte download for the KV is slow, but maybe some objects are taking longer. So having metrics on how long does each individual get takes me, how long is each individual set taking me, what's the tail latency there, how long are the exists taking when I'm doing prefix checking for what prefix are actually available. So all of those things to kind of dive deeper into what is causing that end-to-end slowness help you identify what are the bottlenecks, which then you can go and tweak. And then you got to lather, rinse, repeat, and run the clinical benchmark again to do a before and after test.
I remember getting trained in some of this in high school and college
Yeah.
biology, actually.
Yeah.
You know, you write down your hypothesis, you have to clinically document all the parameters and all the environment upon which, because it needs to be reproducible by someone else or by yourself tomorrow.
Yep. Yep.
And then you need to document the axes on which things are changing and make sure that you repeat the experiment a few times to make sure it wasn't a fluke.
Yeah.
Sometimes in distributed systems, there's noisy neighbor problems, and you can get a lot of unexplainable effects. You mentioned observability. The observer effect, especially at low latency,
Yep.
is real.
Yeah.
As soon as you start to observe something, the parameter upon which the bottleneck changes because you're adding an extra system component. Taking away that observability component sometimes can improve your performance. And then you've lost a certain level of visibility into what's happening.
It's a trade-off, right?
Yep.
When we were first getting into the 100 microsecond latency space, one of the first things we found was our metrics were actually causing the delays. And the way we validated that, instead of going and optimizing the metrics to begin with, we just turned metrics off and ran the test with and without the metrics, and we were able to see the delta. And this is not to say our metrics are bad or good, but it's just to say, like, this is how you run an experiment to decide whether something is worth optimizing or not.
And a lot of the time, performance is a continuous spectrum. It is not black and white. Even with KV Cache, you are paying for some form of storage, whether it's DRAM or disk or something else, in exchange for the most part, GPU, because GPU is really expensive. And sometimes you may even be willing to trade off some performance, right? Some level of performance.
To get more throughput.
To get more throughput, because that's what helps your business.
Yep.
Because
Or stability.
Yeah, exactly. Stability from bursty traffic. So performance is a all-encompassing concept that's not just one single dimension of as fast as possible. It's how fast can I push my system within the parameters of budget and stability, predictability, and other things like, the how many humans are around to operate it.
Yeah. Yeah. I mean, this is where SLOs come into play.
Yes,
and
exactly.
You have to be very well aware of what your production SLOs are, so that when you're designing the system and you're characterizing it, you can meet the SLOs. And there's every once in a while, we run into customers when we ask them, okay, well, what is the objective that you're trying to hit? And oftentimes they say, no, we just needs to be as fast as possible. And in all my years, I've heard that statement 100+ time, and I've only it's one scenario where I'm like, okay, you're right. You want this to be as fast as possible. But for the most part, having a concrete goal almost always is better than just saying as fast as possible. I'm curious how you envision the software stack changing, because until recently, all the models were primarily, they just ran best on the NVIDIA chipsets, and they are amazing. And only if I can get my hands on enough of them. But what are you seeing on the hardware side?
NVIDIA obviously has a head start, but there's a lot of companies trying to get into the same space. As anybody says, when you have a giant, you have a bunch of Davids trying to take over the Goliaths. And NVIDIA is an amazing company, and I'm sure they'll keep innovating. But there are advantages to being small and nimble and being able to experiment. I mean, we mentioned a few of them, like Talos, that burned the model, by the way, in an incredible amount of time compared to what you would normally think about fabricating an ASIC chip in years.
Yeah.
They're able to compress it down to 3 months or something incredible. Now, models are coming out every week.
Yeah.
Right? So there's kind of
You got to find the balance, right?
Yep,
Where
there's a never-ending race. And there are other interesting areas that people are exploring, like super tiny models that do a very specific thing. You talked about being in the critical path. Let's talk about something like anomaly detection, fraud detection.
Yep.
If you're able to tune your model to do a very specific thing, do you really need GPUs at that point? People are starting to get creative about hardware and where you can, run these models. So I think that that landscape, I don't think I can even imagine the direction in which it might go, but I think it'll be very exciting. And I think that we're always being pushed to be more creative and to innovate more on that layer. And then subsequently, that would drive the layer above it to keep up,
Yep.
right?
Yep.
To enable it. Some people would say to get out of the way. Well, you still need
Software
the
needs to get
software.
out of the way.
Software
Yep.
needs to get out of the way of fast hardware. But really, I think we should think about it as complementing, enabling it, right? You still need to grab the relevant data to feed it to the hardware, right? The model itself is not context aware. It's
No,
stateless.
it's
So you need to give it the relevant data in as fast as manner possible. And today, a lot of the software is bespoke.
It
Right?
is.
So we have the benefit of being dominated by NVIDIA chips. So everybody's building on those. But that's not going to be the end of it. So we're going to have to keep building software that follow the same principles but work across all hardware.
I think so, but all of the hardware just seems to be sold out. You look at CoreWeave being sold out for,
Yep.
they just can't make things faster than
Years.
they can sell. And I think the same is true for Cerebrus and Trainium and so forth. So people are doing very incredible, interesting things. Like the Cerebrus announcement recently was pretty interesting, where in Amazon, they'll use the Trainium chips to do the prefill.
Yep.
And then they'll do the decode on the Cerebrus gear.
Because that's where their advantage is. So if you're resource constrained, you should spread your utilization.
Fair. Yeah, like purpose-built hardware, employing it for very specific use cases and being able to service more customers. It's an exciting era. I think those types of architectures make our technology even more relevant. And our team is super excited about what we're going to be able to pull off in this space, especially as we start to build our ultra low latency inference stack.
Yeah, for sure. I think that our team is pumped up about reapplying these lessons over and over again that we've accumulated for years. And most of them have been battle tested in production with our customers at tens of millions of TPS scale. The sky's the limit for us.
That's right. Super excited to be a part of tech in this era, to be a part of the low latency tech. So,
all right.
Thanks for taking the time to chat.
Thank you. It's always a pleasure. Until next time, everybody.